Today we will be looking at the physical interpretation of the derivative. In other words, how would you interpret a derivative practically in terms of everyday language? So there are plenty of examples where you might see derivatives used in biology, economics, business, physics, engineering, you name it. And when you see those examples used in a text, you'll want to look at the notation and be able to interpret practically what they're trying to convey, what meaning an author might be trying to convey by using a certain notation. Our first example is an example from physics. It's the motion of a particle along a one-dimensional axis. So this is basically one-dimensional particle kinematics. So if we look at motion of a particle. So here a particle is just a small dot. It's an idealized concept in physics where you have a particle that sometimes it has a mass and it's just moving around in space. So today we'll just be focusing on one-dimensional motion. So 1D. In Calculus 3 we'll look at particle motion in higher dimensions, and actually we might see a little bit of that before Calculus 3. So here we think of the position as a function of time. So the position is a function of time. And usually we'll say x of t. So this would be the position of the particle at time t. So normally you're used to seeing x as the independent variable. In other words, it's the input variable. Here we're using the variable x as the dependent variable, or the output variable. Instead of saying y is equal to a function of x, we're saying x is a function of t. So if we draw this on a graph, x would be the vertical axis and t would be the horizontal axis. And if we have something like this, like a sinusoidal curve, something, let's say this is 6, maybe this is 2, 4, just like that. We can interpret this as where the particle is at what time. So if we have our one-dimensional axis, at time 0 the particle is right here at 6. A little while later it's at 4, then it's at 2, then it's at 4 and 6. So the particle's moving back and forth. So if you're pacing back and forth like this, it's from 6 to 4 to 2 to 4 to 6, back and forth, when you graph that, when you graph your position as a function of time, it might look something like that. Okay, so that's the position as a function of time. Now the derivative of the position is the velocity of the particle. So the derivative, x prime of t, is the velocity of the particle. And we'll see why this is true in a moment. So first let's think about the average speed. So let's graph x t, 3 o'clock, 4 o'clock, 5 o'clock. Let's say you're in a car trip. So let's say you're at mile marker 20. And at 5 o'clock you're at mile marker 160. Now you might start off at a certain pace. So first of all, your average rate of change, without even adding any other detail, will be x of, let's say, 5 minus x of 3 over 5 minus 3. X of 5 is 160, x of 3 is 20 over 2, so that's 70. And the units of the x are miles, and the units of t are hours, so this is miles over hours, so miles per hour. So 70 mile per hour. So maybe we can start off at that average, and in fact that average speed is just the slope of the line that connects those two endpoints. But let's say our graph starts off, but then you speed up a little bit, and then you slow down, and then you stop, and then you speed up. You're going slow, and you're going faster, going really fast, slow down to 70, Going faster, slow down, faster, slow down. Something like that. When I'm going faster, I have a higher incline because I'm traveling greater x distance for the same amount of time. Right? So maybe my actual curve looks something like that. Maybe I even stopped the car and went backwards, in which case instead of increasing, the function would be decreasing for a short while. But we can see that the average rate of change is simply your average speed, right? Because if you say I traveled 140 miles in 2 hours, well, your average speed was 70 miles per hour. You do 140 divided by 2. So the average rate of change represents speed. So it only makes sense that the instantaneous rate of change represents velocity. So when we take the average rate of change and then take the limit as, the right endpoint moves closer and closer and closer to the left endpoint, so we're looking at the change in x at one moment, at one instant in time, we get the instantaneous rate of change, which is the velocity, right? So the derivative has the same units as the average rate of change. So the units of the derivative are going to be, the units are going to be just miles divided by hours, because again, x prime of t is going to be the limit as h goes to 0, x of t plus h minus x of t all over h, right? So for any particular single moment in time, so if you fix t, so think of t as fixed, maybe t is, right here, just for the moment, and then after we take the limit, it then varies because we can do this for any point. But for a fixed t, we're looking at the average rate of change between t and t plus h. So this would be t plus h, and this would be t, right? So you get the average rate of change, and then when you shrink h to 0, you get the instantaneous rate of change, but the units are not affected by the limit, right? So if this is miles divided by hours, after you take the limit, you still get miles per hour. So x prime of t gives you exactly the instantaneous rate of change, which is, in this example, the instantaneous velocity. One other thing is that if x prime is positive, it means it's a positive velocity, which means the particle is moving in the positive x direction. So if x prime of t is greater than 0, so particle moving towards increasing x values. Right, so it's moving towards positive infinity. If x prime of t is less than 0, the particle is moving toward decreasing x values. Right, so it's heading in the direction of minus infinity. So the sign of the velocity tells you the direction, whether it's towards the positive values of x or towards the negative values of x. If you're looking at a standard one-dimensional line like this, and you're thinking of the particle like moving around on this x-axis, a positive velocity means motion to the right, and negative velocity means motion to the left. So the key point from this example is simply that the derivative of the position is your velocity.